Imagine you've got a Ferris wheel. Okay. Looks like this. Okay. So a Ferris wheel goes around. Okay, maybe like that. Okay. And let's take the coordinates of this cabin here. X0, Y0. Okay. Obviously, this Ferris wheel will rotate, and you could ask yourself, like, what would happen? Like, what would be the coordinates if you rotate by 120 degrees? Okay. What would be the coordinates if you rotate by 180 degrees? What would be the coordinates if you rotate by 360 degrees? Ah, that's easier, right? With 360 degrees, you'll be back to where you were before. So we see that as we rotate, the coordinates, they change, but eventually they repeat themselves. After a full turn, you're back to where you were initially. So this is what we're going to look at here. We're going to look at those coordinates and find out what they are if we rotate by some angle. And obviously here we can rotate by an angle that's more than 90 degrees, like 120 degrees, and it makes complete sense. So for that, we're going to need to consider the coordinates for rotations that are beyond 90 degrees. And those coordinates are going to link to the cosine and the sine function. So we're going to be looking at cosine and sine for angles that are beyond 90 degrees. So we're going to take a look at how these coordinates can vary as the angle varies. So we're going to look at how sine and cosine vary as the angle varies. And if we're looking at a quantity that varies with respect to a certain variable, we're going to look at a function. Okay, so cosine and theta and sine of theta in this section are being looked at from the point of view of functions. We're going to look at how cosine is changing as theta changes. So maybe quickly recall that cosine and sine, if we're on the unit circle, so it's a circle of radius 1. And you're going to tell me, well, the Ferris wheel probably doesn't have a radius of 1 meter or 1. Okay, but we can actually easily recover the coordinates on the Ferris wheel if the radius is not 1. Okay, by looking at the coordinates on the unit circle. So this is something we can actually do. So here, imagine that the angle is theta. This is going to be x, y, and those values of x and y correspond to the cosine of theta and the sine of theta. Also, the arc length here, so the length of the arc subtended by the angle is theta if we work in radians. Okay, so this is only going to work if we work in radians. Okay, so for the unit circle, x squared plus y squared is equal to 1. So that means that cos square of theta plus sine square. Actually, I'm not going to write it like that. So you're maybe are wondering what I'm doing here. There's actually a very compact way of writing cos theta bracket squared, but for now I'm going to keep writing it like that. Okay, so maybe for your information, eventually cos square, because it occurs very frequently that we're squaring trig functions, there's a notation for that, and we write it as we put the square in between the symbol cos and the argument, which is the angle here. So it's kind of funny because it's like having f of theta that you want to square, but the shortcut would be to put this. And we don't do that for functions in general. Okay, we don't use that notation, but for trig functions we use it. Okay, we put the squaring symbol in between the symbol for the function and the argument. So we can actually write this like that. So it avoids having like parentheses all over the place. But for now, I will keep writing it like that. Okay. So this is what we pretty much know. We know that when we start here, this is 1, 0, and when we end here at 90 degrees, it's 0, 1. But we could actually keep on going. So that's the point here. We could actually have an angle that's actually beyond 90 degrees and still talk about the cosine. So maybe this is, I don't know, alpha here. This would be cos of alpha, sine of alpha. Okay, and if you think as theta being a variable, okay, something that can actually change, okay, you could think also of this as being like an alpha that has changed. So this would also be cos of alpha, cos of theta, sine of theta. It's just that theta is allowed to change here, and it's a variable in the problem. Just like in the Ferris wheel, you're allowed to change the position of the cabin by changing the value of the by rotating it around the Ferris wheel. So here are different values of theta and different values of cos of theta, and just by creating this table we immediately see that cosine can be considered as a function of theta. So when theta is 0, this is where, when we're here, the cosine is the x-coordinate, it's 1. Okay. After that, we've seen some special angles. Like at pi over 6, the coordinate decreases slightly, right? Because as you start here, if you look at your x-coordinate, as you rotate a little bit, they're going to get smaller here. So the next one is root 3 over 2. So remember, how do you remember this? This creates a triangle, and the length of the base should be higher than the length of the height, and we know that the coordinates here are going to be root 3 over 2 or a half, so you choose the largest one for your base, so for your cosine. At pi over 4, this is where cosine and sine are equal to each other, and this occurs if they are equal to root 2 over 2. At pi over 3, it's root 3, it's 1 half. And at pi over 2, so this is when we're up here, the cosine is, as you can see, the x-coordinate of that point is 0, so 0. And then we could keep on going. You see, for example, if we're at pi is 180 degrees, so 180 degrees is when we turn, well, we do a half turn, so we end up here at coordinates minus 1, 0, so it would be minus 1. Then we have what? 3 pi over 2. 3 pi over 2 is when we're here. So when we're here, if theta is there, the coordinates of this point are 0, minus 1. So the cosine is 0 again. So notice how it's 0 at pi over 2 and at 3 pi over 2. And at 2 pi, we've done a full rotation, so we're back to where we were before. So we're back at 1, 0, so the cosine is back to 1. Okay, and we could keep going. Actually, we could keep rotating. Okay, and this would create a function for cosine. So if I want to graph cos of theta, and I'm going to do this actually in more detail in the next chapter. So I'm going to do it quickly here. So the values, obviously, they alternate between 1 and negative 1 because the x-coordinates, which are the values of cosine on the unit circle, right? They oscillate between, or they change between 1 and negative 1, right? You can't have an x-coordinate that's larger than, in absolute, than the radius. So for our cosine curve, like here are some pretty important angles. I'll just write down like pi over 2, 3 pi over 2, actually pi, 3 pi over 2, and let's extend this line. This would be 2 pi, and it would keep on going afterwards, by the way. So at 0, we're at 1. If you look at so here, I'm just going to illustrate those points here. So this one, this one, this one, this one, and this one. So at 0, we're at 1. Then at pi over 2, we're at 0. At pi, we're at minus 1. Here back at 0, and here back to where we were initially. And we're going to see why that is, but the curve is kind of like that. It's got this S shape, like a x squared in some way. Okay. It's got what we call a change of concavity in many places. And then it repeats itself because the wheel, Ferris wheel, keeps turning, right? So it just repeats itself. So it's, and this, we're going to see this again in greater detail, but it's called a periodic function because it just repeats itself. Right now I'm looking at the curve when the angles are negative. So this is for clockwise rotations. So this is what cosine would look like. Cosine. Okay. So obviously it's defined everywhere. So its domain is all real numbers, all real values of angles. But the range, okay, if we look at the y values that are covered, it's between -1 and 1. Okay? And the same could be said about sine. It's a function that actually has a graph that's very similar. Actually, you know what? I think I'm going to add it because sine actually starts, you look at the y coordinates now, so it starts at 0. Look at the this y coordinate here. It starts at 0 right there. Okay. At pi over 2 we're at 1, and then this is annoying. Let me try this. Okay. And then we're back at 0 here. So it actually goes like that. At 2 pi we're back to where we were initially, and then it keeps on going like this. So obviously there's a strong link between the graph of cosine and sine. So this would be y equals sine of theta. And it has the, so maybe I should write domain of cosine, range of cosine. Here the domain of sine is all real numbers again, and the range of sine is also between -1 and 1. Okay, we're going to look at this graph in greater detail in another section. So maybe let's quickly look at an example here. Let's say if sine of theta is 3/7 and theta is in the second quadrant. Second quadrant, remember, first quadrant is kind of hard to explain here. First quadrant is where x and y are positive. Okay, this is the second quadrant, third quadrant, fourth quadrant. So we're going to be asked to find just cosine, but I could ask you also to find the other trig functions. So how do we do this? So maybe one thing to notice, actually this picture with the quadrants, I'm going to actually make it a little bit bigger because I want to add some other information. So first quadrant, second quadrant, third quadrant, and they're typically written with Roman numbers. In this quadrant, okay, if I've got an angle, okay, the sine is obviously positive, cosine's positive because it corresponds to the x and y coordinates. Okay, so here sine is negative, positive, cosine is positive. Over here, okay, as I keep turning, okay, then I'd have coordinates for sine and cosine that are not all positive now. The x coordinate is now negative. So cosine is negative while sine is positive. Over here, in the third quadrant, sine and cosine are both negative. And over here in the fourth quadrant, cosine is now positive, while sine is negative. This is not something you need to remember by heart, right? It's common sense if you look at where those quadrants are located in the Cartesian plane. So if we're in the second quadrant, we know that our sine is positive, which makes sense, right? They gave us 3/7. We'd question we'd wonder if the question would be correct if the sign would have been negative, like something would have been wrong. We can't be in the second quadrant and have a negative sign. So sine is positive. Okay, that's reassuring. We know the value of cosine we're looking for is going to be negative. Okay, so one way to get the value of cosine, but I'll show you different ways later on, is to use the identity, which says that cos squared plus sine squared equals 1. So we don't know what cos theta is, but we surely know what sine of theta is. It's this. And then we solve for cosine. So solving for cosine squared first, maybe, we get 1 minus 9 over 40. 7 squared is 49. So we get 49 minus 9, we get 40 over 49. Okay, so that's cos squared. So of course cos theta will not be positive. Careful, like if we square root 40 over 49, we'll get the absolute value of cosine, right? This is due to the fact that if you've got x squared equals k, x is the absolute value of k, or if you prefer, x is plus or minus k. Okay, so we've been using this throughout the course. So here, absolute value of cosine is the square root of 40 over 49, which ends up being what? It's the square root of 40 over the square root of 49, so this is something over 7. Square root of 40 is 4 times 10, so this is going to be 2 root 10 over 7. And our cosine, is it positive or is it negative? This is where we have to decide, like when we take out the absolute value, is cosine going to be positive or negative of 2 square root of 10 over 7? And this is where you come back to your diagram here in the second quadrant. This point here will surely have an x coordinate that's negative, right? Because we're to the left of the origin, so it's going to be the negative of that. And that's the value of cosine.